Welcome to our exploration of aluminium remelting. In today's video, we delve into the physics and principles that govern the operation of aluminium remelting furnaces. The primary type of melting furnace used in this process is the gas reverberatory furnace, which can be stationary or tiltable, allowing for efficient remelting of aluminium. A tiltable aluminium remelting furnace. Four mechanisms transfer heat to the aluminium charge in the furnace: heat radiation from the furnace lining, combustion gas thermal radiation, direct flame radiation, and convective heat transfer from hot gases. Heating by radiation is the main source of heat in a reverberatory furnace, although optimizing all heat transfer mechanisms at different melting stages is crucial for efficient operation. Solid aluminium has excellent thermal conductivity, allowing for rapid heating at the beginning of the melting cycle. In contrast, liquid aluminium has significantly lower thermal conductivity. The energy needed for remelting includes heat to raise temperature, the heat of fusion, and heat to get molten aluminium to the desired casting temperature. The efficiency of the melting furnace relies on how well the solid charge absorbs heat before it sinks below the melt surface, which is vital for effective melting. As cold metal enters the hot furnace, it absorbs heat from combustion gases, leading to effective heat transfer despite low temperatures of furnace off gases. Solid aluminium is denser than liquid, so it tends to sink in the molten bath. However, if the surface charge is too large, it may float due to surface tension. Once submerged, heat exchange is limited by thermal conductivity of the molten aluminium, requiring efficient heat transfer mechanisms to melt the charge. Increasing the melt's temperature can lead to more dross formation, which can insulate the heat, but also helps absorb heat radiation. Finding a balance is key. A thin layer of dross can be beneficial, but if it becomes too thick, it insulates the melt and increases the surface temperature needed for further heating. Generally, deeper furnaces require more energy and have higher waste. An optimal melt depth of 500 to 600 millimeters is recommended for efficiency. Mechanical mixing tools are often used to increase heating rates, but they can cause dross formation and disrupt the steady state of the melt. For larger operations, advanced stirring systems like melt pumps are essential to maintain a uniform temperature without excessive dross production. Thanks the authors whose works we used in preparing this video. Thank you for watching. Don't forget to subscribe and like our video.